Okay, so what we're talking about here today is when you have the volume of a solid rotated around some axis, and what do you do if you cannot use disks or washers? So for example, we have this function here, and we're saying we're going to rotate this area between f of x and the x-axis about the y-axis. So we are rotating in this direction. Okay, so first thing I'm going to do is attempt to draw a three-dimensional figure. Okay, so I'm going to make it symmetric on both sides of my axis. And then this is going to be kind of a strange looking figure. So if you think about like what the outside, so here's the base. The outside that's facing towards you is going to be this piece right here. Oh, that. And you would kind of only see this. You would not actually see what's going on inside, right? Because you have those dips. So that's kind of what you would see. I know it's like hard to visualize here. And then coming up from the inside, you would also see these pieces coming out. And those pieces are also rotated. So something like this. Okay, where you see those like peaks are rotated as well. So it's gonna look something like this. I know it's hard to visualize here, but you would only see really the outside of this figure, and then like the higher peaks inside kind of popping out of it, at least from this point of view. So here's the thing. I'm going to go back to just looking at this without the 3 dimensions. When you try to use disks, so let's pick a random place like right here. Let's say I wanted to turn this into a disk. Okay, well, I've got a few problems here. I've got this radius and I've got this radius. Like for this whole y value, I've got a lot of different radiuses to look at because it's going to be counting. This piece needs to be counted, and this piece would need to be counted at that particular y value, but I wouldn't count this piece and I wouldn't count this piece. So I can't really use a washer here because it's going to be way too complicated. I have too many radiuses basically to worry about. Another thing to consider is if you were using the disk or washer method, the width at one of these places is not dx, dy, which would mean I'd have to solve this equation in terms of y. And I would have to find a way to solve for x equals and then have an equation in terms of y. There's no way for me to do that here. I would need to like figure out how to factor it and then get x by itself. There's too many x's, too complicated. So I'm not able to use the washer or the disk method in this case. So instead of thinking about it as a bunch of disks and washers, I'm going to think about it in a totally different way. And the way I want you to think about it is, what if you took like cans? And I'm saying cans because normally if we were in class, I'd actually have cans to show you, and you stacked them inside of each other. So I have like a small can inside a slightly larger can, and the can is empty. It's not filled in. Inside a slightly larger can. So these are called shells. And so the shell method is using cylinders like the disk and washer methods were, but they're going to vary in heights. So I would think about this figure as really small cans all the way down here. All really small cans inside slightly larger can, inside a slightly larger can, going all the way out until you got here. So that would be one of my larger cans, even out here. Sorry, I know this is a messy drawing, but you get the idea. So we're not using washers and stacking them up. We're using cans or shells and we're stacking them inside of one another, where the thickness of the shell is really, really small. Okay, because we're using an infinite number of these cans that are stacked inside of each other, and the thickness of those cans is going to be infinitely small. So that's the shell method. Let's go ahead and generalize this in a formula. First, by thinking about what is the volume of one of these shells. So if you think about a shell is a cylinder that is completely empty. So if you were to unravel the shell, you would end up with just a rectangle. So the way I normally, if we were in class, I would show this to you, is if you take a piece of paper, just a regular rectangular piece of paper, and you wrap it around, it creates a shell. And you can stack those shells, those pieces of paper, one inside the other. And you can create a three-dimensional figure that way with enough paper. So the volume of a shell is going to be the area, the surface area of this rectangle, times the thickness of the piece of paper or the thickness of the shell. So remember I said we want the thickness of the shell to be infinitely small. So the thickness is going to be dx or dy. Okay, so the thickness is approaching 0. Then we have the area of the shell. So that's the thickness. Okay, that's how thick it is. Okay, but then we need to multiply that by the height and the base of your piece of paper, basically, your rectangle. So the height of the rectangle is the same thing as the height of your cylinder. And then if you think about the width of your rectangle, so the area of your rectangle is just base times height. So the base here is the same as this all the way around. In other words, it's the circumference of the circle. So the base of that piece of paper, when you bend it around to create a cylinder, create a shell, that base is going to be the circumference. It's going to become the circumference of that circle. Now the circumference of a circle is 2 pi r. So the base is also going to be 2 pi r. So the volume of a shell is 2 pi r h times the thickness. And we are going to be able to replace the r, the h, and the thickness with values from our function. So going back to our notes, we're going to do these 3 examples. So as we said, the volume of a shell is equal to 2 pi RH times the thickness. Just think about a shell as a piece of paper that is wrapped around. So it's the circumference times the height and then times the thickness of the paper. So if I am rotating the area between F and G around the y-axis, in this case, it's going to look like this, and like this, and I'm going to take one representative rectangle, the area between my 2 curves, and that is going to be repeating over here, and my shell will look like this. Okay, so that's just one shell, but remember, it's an infinite number of shells that are stacked in one inside of the other to create this solid figure. So let's start plugging in what we know for the radius, the height, and the thickness. So the radius is the distance from the center of rotation or the axis of rotation to where the outside of the shell is in this particular case. Now what's nice about this is no matter where your shell is, whether I have this shell or if I have like this shell way out here, if you are rotating around the y-axis, the distance between the axis of rotation and the outside is just a distance of x. That's it. Like if I'm here, that distance is 1.5 for my particular case. Or if I'm out here, it's 2.5. So the radius is just whatever x is when you are rotating around the y-axis. The height is the next thing I need to plug in. The height of the shell is the distance between f of x and g of x. It's the area between the curves, right? So the height is just going to be the upper function minus the lower function. And then the thickness is the thickness of your shell, which in this case is going to be dx. So what's nice about the shell method is that if you don't want to have to use the washer method and rewrite everything in terms of y, we can leave everything in terms of x, because the thickness is dx, the radius is x, and the height we can also just leave in terms of x. So the volume ends up being 2 pi times the integral from a to b, whatever your bounds are going to be of your area between curves. So if I'm like from here to here, right, this would be my a and this would be my b. So it's the area from a to b of r, which is just x, times your height, which is f of x minus g of x. And then the thickness is dx. So notice that nothing is squared here. It's 2 pi rh times the thickness, where the radius is x and the height is the distance between the two curves. For this next picture, now I'm not rotating around the y-axis, so I do have to make a minor change. So my graph will look like this. 1, 2, 3, 1, 2, 3. 1.5. And 1. Okay, so it's kind of this area here. And let's say my A is whatever, it's here to here. So that's like here to here. So I have all of this area rotated around to create my three-dimensional figure. Try that again. I do not have the steadiest hands in the world. So it's kind of like what the outer shell would look like. And then when we're here, the inner shell would be here. And my representative shell, I'll go ahead and draw like right here. So again, an infinite number of shells that are stacked within one another. So it's still 2 pi rh times the thickness. So let's start with my radius. My radius is the distance from the axis of rotation to the area between the two curves. So here, this is going to be a little bit different because my radius is not going to be just x. I have to take into account that there is this distance of c. So this is a distance, so x is equal to c, it's like -1 in this case. That's that distance here. But then my x distance is always the distance from the x-axis, which is here. So if I'm at my representative, from my representative shell, I'm starting at x equals 1, so I also have this right here. So in order to count my radius, I have to take both things into account. I have to take into account the -1, and I have to take into account the +1. So if I'm using these numbers, -1 and +1, that's a radius of 2. So how am I going to get a radius of 2 out of this? Well, just like we did for washers, you always start with like the outer piece minus the inner piece. And outer is going to be the one that's more to the right, and then the inner will be more to the left. I'm sorry, I said outer and inner. I meant upper and lower. It's going to be the upper minus the lower. So this is going to be the x value, because again, x is the distance from the x-axis, the y-axis, not the x-axis. And then that's going to be minus c. So for example, here I should have a radius of 2, because if I plug in x is equal to 1 and I plug in c, which is -1, I get 1 minus -1, which is 2. Likewise, if I were like out here, if I was at like 1.3, right? The 1.3 comes from the distance to the y-axis, so that's 1.3, but I still have this extra 1 here because that's the distance all the way to the axis of rotation. So like this is 1, this is 1.3, that's a total distance of 2.3. And the way I can get that is 1.3 minus -1, which ends up being 2.3. So if your axis of rotation changes, and it's not just the y-axis, you do have to change your radius. But that is the only thing that changes, which is nice. The height is still going to be the upper minus lower function. And the thickness is still dx. So the volume is 2 pi times the integral from a to b, whatever your bounds are. The radius is x minus c, but the height is still f of x minus g of x, and the thickness is dx. So the only thing that we had to change was the radius. So if your radius, your axis of rotation changes with the shell method, then your radius will also change. And then lastly, what happens if your axis of rotation is on the right-hand side? So if I'm taking this area and I'm going from A to B and rotating that around. So it's going to be this whole area, rotate around, creates that area. And let's draw some shells here. That's my outer shell. My inner shell would be like right here. And then my representative shell is going to be right here. So that's going to be like this. So, again, the height is actually going to be the same. It's still going to be the area between f of x and g of x. That doesn't change. But my radius does change. So recall that x is the distance to the y-axis. So like this, if I'm right here, if I'm at like 1.2, that's this distance right here. But what I need is this part right here is my radius. It's the distance between the axis of rotation and the outside of the shell. So how can I find that? It's going to be, again, kind of the upper minus lower, or the most right minus the most left. So in this case, it's just going to be c minus x, because c is this total distance. So like c is 3 in this case. So that's the distance to the y-axis. X is the distance right here. So the radius is going to be c minus x. Okay. The height is still f of x minus g of x. So the volume is 2 pi times the integral from a to b of c minus x times f of x minus g of x. So I'm running out of space here, dx. So that's the shell method. This one is kind of the most important. This is the one that you'll probably want to use the most often. These do come up. So again, just remember that if your if your axis of rotation changes and it's not just x equals 0, it's going to be the radius that changes, and it's going to be the one that's on the right minus the one that's on the left. So it's going to be either c minus x or x minus c, depending on if the shell is more to the right. The outside of the shell is more to the right than the axis of rotation, or if the axis of rotation is more to the right than the outside of the shell. But the first example is the one that's most important. And I don't remember if I said this before, but the shell method is not a requirement for the AP exam, but it does make things a lot easier in certain situations. So for example, remember when we did these with the 815 section, and they were super long and complicated, and you had like 2 washers that you had to add up the areas for, and it was just kind of like a big mess. Well, if we use the shell method, it actually simplifies things for us in a few different ways. If I rotate around the y-axis, I end up with this area, and so my shell is going to look like this. Okay, it's not perfectly symmetrical, but you get the idea. So that's going to be volume equals 2 pi, and then it's going to be the area starts at 0 and ends at 3. And we can keep everything in terms of x. We don't have to rewrite it in terms of y like we do for the washer method, because the thickness of this shell is dx. So I'm allowed to leave everything in terms of x. So my bounds are in terms of x. My radius, because I'm rotating around the y-axis, is just x. The height is going to be the distance between the curves. And again, I don't have to rewrite them in terms of y. It's just going to be h of x minus k of x. The thickness is dx, because again, it's 2 pi r h times the thickness. So my radius is just x when I'm rotating around the y-axis, and my height is the upper minus lower function. So that is way easier than having to use the washer method, which is what we did before. Even rotating around the line x equals 1 for this problem is still, x equals negative 1, I should say, is still a lot easier to look at. So here. Okay, so my it would look like this. I have a representative shell like right here. So that's going to be volume equals 2 pi. The values of my x are still 0 to 3. Even though my axis of rotation has changed, my area between the curves has not changed places. This is still the area between my two curves. So I'm still going from 0 to 3. The only thing that's going to change here is the radius is not going to be just x. So remember, it's going to be either the axis of rotation, x equals c. It's going to be c minus x or x minus c. So just look at where the outside of your shell is in between the curves that you have graphed. Again, I'm not going over here for the outside of the shell. I'm always staying where the area between the two curves are. The area between the two curves are between 0 and 3. So that, if I'm at my representative shell, that is more to the right than x equals negative 1. So that means my whole radius would be my x value plus 1, right? So x plus 1. In other words, x minus negative 1. It was x minus c. Because I had a distance of 1 to the x-axis. I'm sorry, to the y. I keep saying x-axis. To the y-axis, that's a distance of 1. And then x is also the distance from to the y-axis. So I have to add those two in order to get an entire radius. So that's x plus 1 is my radius. But the height is still going to be the upper minus lower functions. I do not have to rewrite them in terms of y because the thickness of the shell is dx. So shell method is not totally required, but as you can see in some instances, it makes things a lot nicer. So you don't have to know it, but it's nice to know it.